Okay, so this is still titration, but today is just weak acid or base titrated with a strong acid or base. So one of the entities is weak. Now, what difference does this make? Well, it makes a huge difference. The calculations today will be way more complicated. Equilibrium has to be considered because there are weak acids and weak bases. So let's consider this first of all. You have a weak acid titrated with a strong base. So you have 20 milliliters of 0.3 molar acetic acid. Okay, the acetic acid is a weak acid. It is in the flask. It is titrated with a standardized solution of 0.3 molar sodium hydroxide, which is the strong base. That's in the B red. That's the titrate. Because acetic acid is a weak acid, it will have this equilibrium with water. Okay, how would that change anything? Well, the equilibrium will favor the reactants because you have a small Ka. So most of the entities at equilibrium will be reactants with very little product. So because the Ka is 1.8 times 10 to the negative 5. When you start to add hydroxide, this neutralization reaction would occur. Okay, the acid plus the hydroxide, the base, you will produce the acetate ion. So basically the OH will just take a hydrogen from the acetic acid and then you make water. Excuse me. So in a way, acetic acid is being turned into the conjugate base acetate via this neutralization reaction. Okay? And this is a one-way reaction. It is not in equilibrium. Excuse me for a sec. All right, so it is not in equilibrium. It goes in one direction, and this will go to completion. So despite the fact that acetic acid is a weak acid, it does not 100% ionize, but it can still be consumed completely by a base. All right, so without the base, the equilibrium lies on the left side. But as you add more base, the hydroxide will react with more and more acetic acid to produce the acetate conjugate base, which is a product. So you are shifting the equilibrium to the right by adding more base. All right, a way to look at this is by adding hydroxide, you reduce the amount of hydronium, the H3O in the product of the equilibrium. They will form water. As you reduce hydronium, Le Chatelier's principle would then favor the production of more hydroxide by shifting the equilibrium to the right. So more products will be made to make up for the lost hydronium. As a result, acetate, the conjugate base, also rises as you consume more acid. Eventually, you will consume all of your acid. You will shift the equilibrium to the right so much that the equilibrium will no longer exist. You will have a one-way reaction. Okay. If you have that, then you basically consumed all of your acid with your base. There is no difference between a weak acid and a strong acid in terms of how much base I need. So here is example 1. Example 1 is a titration question between a weak acid and a strong base. So you have 25 milliliters of hydrofluoric acid, HF, which is a weak acid, titrated with 0.4 molar standardized sodium hydroxide solution. That is a strong base. So determine the concentration of the acid if 16.5 milliliters of titrate is required to reach the equivalence point. Now, questions like this, where you're given 3 numbers asked to solve for the final one, in this case, the concentration of the weak acid, there is no difference between a strong acid and a weak acid. All right, the equilibrium does not matter because a neutralization reaction goes in one direction. In fact, in grade 11, when you learn titration, you learn how to calculate stuff like this. I never bothered telling my grade 11 students which one is a strong acid, which one is a weak acid. I just never mentioned it because it didn't matter. It didn't matter if it was strong or weak acid. It's the same strategy. So in order to solve this problem, you have to write the balanced equation, HF plus NaOH. You have NaF plus H2O. It's a 1-to-1 ratio. So you would, of course, multiply together the two entities that you know the volume and concentration of. So you know the sodium hydroxide concentration. You know the volume of sodium hydroxide. If you multiply them together, you will get moles. You then use the mole ratio to convert to moles of the acid. Divide by volume to get concentration like this. Okay, 60.5 mils, that's the volume of the base, times the concentration of the base, 0.4 moles per liter. Instead of per liter, I have 1,000 milliliters, which is the same thing as per liter. I have mils because I want to cancel the 2 mils. So now, with that calculation, I would have the moles of sodium hydroxide. Because for every 1 mole of sodium hydroxide, I have 1 mole of HF. It's a 1-to-1 ratio. So now I cancel the moles of sodium hydroxide. I have moles of HF. I need concentration of HF. So I have the moles. All I have to do now is divide by the volume, moles per liter. And I convert the 25 milliliters into liters. So I do the division. Finally, you put this in your calculator. You get 0.968 moles per liter. That will be the concentration of that acid. Exactly the same as you would calculate for a strong acid, strong base titration. So this doesn't matter. Okay, when you calculate the concentration or the volume, it doesn't matter. What does matter is when you calculate the pH. If you want to calculate the pH of a titration involving a weak acid or a weak base, yeah, that is way more complicated. So here's what really this lesson is about. We're going to determine the pH of a weak acid titrated with a strong base, as well as a weak base titrated with a strong acid. Basically, it's the same thing, except you have them reversed. And we're going to calculate the pH at 3 different times of the titration. First, before it begins, before you add anything. Second, at the equivalence point. And finally, beyond the equivalence point. Okay, we're not going to calculate the pH before the equivalence point. It used to be in the curriculum. If you check the older version of your textbook, that is in fact in there. And that is very, very hard to do. I don't know for what reason they removed that. So in your new version of the textbook, that's not there. So I'm not teaching it. All right? I don't need this course to be harder than it is. So we're just going to focus on these 3. And don't get me wrong, these 3 are also very difficult. It's just, it gets a little bit easier when you don't have to worry about before the equivalence point. All right, so here's example 2. Excuse me. All right, so in example 2, you have a titration of 20 milliliters of 0.3 molar acetic acid, a weak acid. Titrated with standardized 0.3 molar sodium hydroxide. What is the pH of the solution when the following amounts of sodium hydroxide are added? So A, when you have nothing, you didn't add any sodium hydroxide, so before the titration begins. B, after you add 20, which is the equivalence point. And also C, when you add 35, which is beyond the equivalence point. So here is your neutralization reaction. You have the acid plus the sodium hydroxide, the base. You have sodium acetate, your salt, and liquid water. And you, of course, you know all of these information. You know the concentration of the acid, the concentration of the base, volume of the acid, volume of the base. You do know that. It's just different at different stages. Calculate the pH. Okay, so we're going to break this down one step at a time. But first, let's look at this diagram here. So who's present at what stage? It is very important that you are clear with what is going on in the solution. It is better for you to actually understand what is happening on the molecular level when you perform calculations. So, in the first row, that is for before the titration. You didn't add any base, it's just the acid. Okay. On the left, top left corner, you have the solution before the titration, before equilibrium is reached. So you basically just have water and acid molecule, the 3 acid molecules. Okay. The green, you see there's a hydronium and a hydroxide highlighted in green. Those are produced from the autoionization of water. Okay, that's always there. It is 1 times 10 to the negative 7 moles per liter. That's always going to be there. If you look at all the panels, yeah, it's always there. Okay. Acids will donate their protons, specifically the one on the right. That's now highlighted in red. One of the acids donated a proton to the water. You made a conjugate base and you made hydronium. That is what determines the pH of the solution, not the ionization of water. That doesn't do anything anymore because the concentration is so low. If you have another source of hydronium, you just go with that one. Okay, you calculate the pH from the amount of hydronium produced from the equilibrium of the acid. Does that make sense? This is basically calculating the pH of a weak acid, which we already learned. Now, at the equivalence point, when you add the base, you just add enough to reach the equivalence point, and it gets quite complicated. First of all, at the equivalence point, the amount of hydronium produced by the acid is exactly offset by the hydroxide produced by the base. They cancel each other. They neutralize each other. That's the whole point. That's the definition of the equivalence point. So you have the panel in the middle to the left. Okay, the purple balls represent sodium ions. You see that there are, well, I represented this with 3 sodium ions and 3 acetate ion. That means they have reacted to completion. Okay, this would be like a grade 11 representation of the neutralization. That's it, you're done. But this is pre-equilibrium. It didn't reach equilibrium yet. You think, what equilibrium? I thought neutralization is a one-way reaction, right? Yes. But the conjugate base, the acetates, are weak bases. And they have the ability to take protons from water, and that will reach equilibrium. Does that make sense? So the panel on the right in the middle, you see there are 2 blue molecules highlighted in blue. One of the conjugate base took a proton from water. It accepted a proton because it's a base, and you produce hydroxide. And this reaches equilibrium, and you do have hydroxide in the solution at the equivalence point. So once you reach equilibrium, hydroxide is actually produced because you have a weak base present. And for this reason, that the equivalence point of this titration is not a pH of 7. Okay, last time, strong acid, strong base, the pH of the equivalence point is 7. But if you have a weak acid and a strong base, the pH of the equivalence point is actually basic because you are producing hydroxide ions from that equilibrium. And all we have to do is calculate the concentration of that hydroxide, negative log, get the pH. Okay, so that's quite complicated, but you have to understand what is going on in the solution, what is present in the solution, and what exactly you are calculating. Finally, beyond the equivalence point, when you dump in too much base, well, let's consider what happens. In the bottom row on the left side, you added way too many sodium hydroxide molecules, so that now exceeds the acid. All right, the equilibria are still there. Autoionization of water is still there. It doesn't really contribute much. That's negligible. We can just ignore that. Also, the equilibrium of the conjugate base is still there. Okay, this is before it says pre-stoichiometry, before everything reacts. Because once you add the base, it's going to be there. However, this will react so that you shift the equilibrium of the conjugate base all the way back to the left. And so you have the panel on the bottom right corner. You lose all of the conjugate acid in a way. Okay? The blue disappeared because you increase the amount of hydroxide. Le Chatelier's principle will decrease hydroxide by making more water. So you will actually just get rid of all of the conjugate acid and you purely have the excess hydroxides. Does that make sense? In short, if you add too much, it is no different from a strong acid, strong base when you add too much beyond the equivalence point. What determines the pH? The hydroxide from the excess base that you added. All other entities are insignificant. So all you have to do is just figure out in what volume, how much volume did you add in excess, and how many moles of hydroxide did I just add, and what is the concentration? Negative log. Okay, the last step beyond the equivalence point, there is no difference between this and strong acid, strong base. Okay, but the first two are different. So we're actually going to perform these calculations. I hope these pictures help you understand what are we calculating, what's in the solution at any given stage. So let's start with A. Calculate the pH when you add 0 milliliters of base. So basically just the acid, right? The pH weak acid. You need to write the equilibrium equation of that acid. Acetic acid plus water, you have acetate and H3O. You set up an ice table. What is the initial concentration of the acid? Well, 0.3. The products are 0, 0 because you didn't reach equilibrium yet. This is initial. Change, we don't know. It's X. So equilibrium is just you combine the first two rows, 0.3 minus X for the acid, X and X for the conjugate base, and the H3O. The question doesn't tell you what the Ka is, but that's not a problem. You just take out your table, you look on the table, you find the Ka, and you write the Ka expression. Solve for X. Ka is 1.8 times 10 to the negative 5. How do you know that? Look on the table. The right side is just x squared over 0.3 minus x. You would use the assumption that x is so small that subtracting x does nothing. Okay, you use it because it's simple. It makes the calculation way easier. Just you have to justify it. The initial concentration 0.3 divided by the Ka, 10 to the negative 5. That's going to be a huge number. If you divide by 10 to the negative 5, you're going to get a big number way higher than 100. So yes, you can justify your assumption. You can simplify the equation by dropping the x. Okay, you then rearrange the equation. X equals the square root of the Ka times the initial concentration. You put this in your calculator. You get 2.324 times 10 to the negative 3 moles per liter. So that is X. What does X mean? Well, X is hydronium. Okay, you have to know what is X when you calculate X. It's hydronium, H3O. It's the same as X, the same value. So that means taking the negative log of this number will give you the pH. So negative log of hydronium, you sub the number in, the pH you discover to be 2.63. This is the pH of the sample of acid if you didn't add any base. Okay. Because it is pure acid, it has a low pH, which makes perfect sense. Okay. Any questions about A? Okay, good. This is a review of how to calculate the pH of a weak acid, which was a prior lesson. B is way more complicated, okay? So please get your minds ready. If you add 20 milliliters, which brings it to the equivalence point, What's the pH of the resultant solution? It's not 7. Tell them right now it's not 7. You need to calculate this. So what happens at the equivalence point? If you check out the picture on the bottom, I represent the equivalence point with those molecules. You have a bunch of water molecules, equal numbers of sodium and acetate. Okay, sodium acetate is a 1-to-1 ratio. That's the equivalence point. All the acids were neutralized with all of the base to produce just water. Okay, there's no acid, there's no hydronium, there's no hydroxide. Well, actually, there is. The autoionization of water will occur, and you would have very tiny amounts of hydronium and hydroxide in equal concentrations. But then again, I said that this doesn't matter. They're so low in concentration. This will only matter in strong acid, strong base, because you wouldn't have anything else. That's the only thing you have. With the weak acid, though, because you have a weak acid, the conjugate base of the weak acid is a weak base, you still have a base in the solution. The acetate negative ion, okay, it will undergo hydrolysis with water. We learned about hydrolysis in a previous lesson. It will take a proton from the water, establish an equilibrium like that. Okay, so first of all, the acetic acid plus sodium plus hydroxide, you have sodium ion, acetate ion, and liquid water. The liquid water, obviously, we're not going to consider. What's in the solution? You have Na+, you have the acetate negative, you have the hydronium and the hydroxide produced from water. Okay, again, we are going to ignore those two. So between the sodium and the acetate, the sodium is a spectator ion. It does nothing. So the acetate would then hydrolyze. It will steal a proton from the water. So look at the picture below. One proton will be lost from the water, gained by the acetate. So you will make acetic acid again. And as a result, you rip a proton from the water to make hydroxide. The presence of the hydroxide will make it basic. Okay, thus, the solution should be basic. And our job is to calculate the concentration of that hydroxide, take the negative log, and calculate the pH. Okay, now, this can be very difficult to do, so I'll walk you through the steps. So first of all, we know we have to work with this hydrolysis equilibrium. Acetate plus water, you get acetic acid and hydroxide. Okay, you have to first determine who will undergo the hydrolysis. It's the acetate. You write the equation, you steal the proton from the water to make hydroxide. Okay, we need to solve this equilibrium. This is a base. You produce hydroxide. So we need a Kb value. We don't have the Kb value because we don't have a table with a list of Kbs. We do have a table with a list of Ka, so you can use the Ka of the conjugate acid. Remember how we do this? It's Kw divided by the Ka of the acetic acid. You would get the Kb of acetate, the conjugate base. You look this up. 1.0 times 10 to the negative 14, that's Kw. Divided by Ka of the conjugate acid is 1.8 times 10 to the negative 5. We've already used this number. So this is not new to us. Plug this in, it solves. Kb of the base is 5.556 times 10 to the negative 10. Okay, that's the Kb. Once you have the Kb, all you have to do is set up an ice table, solve the ice table for X, which is hydroxide, take the negative log. Does that make sense? Now, how to set up the ice table is not that simple because you don't know the concentrations to set up the ice table. You need to calculate these numbers right there. So Kb equals acetic acid concentration times hydroxide concentration over acetate concentration, but you don't know any of those numbers, right? So because when you mix the acid with the base, you dilute each other. You need to perform a dilution to calculate the concentration after the dilution, but before the hydrolysis. Okay, so this is very confusing. There are many reactions all mixed in one. There is a neutralization between the acid and base. Concentrations will dilute each other to have a lower concentration than before. Hence, this calculation is required. And then hydrolysis will occur. The weak base will undergo hydrolysis with water to make hydroxide. That is the equilibrium we're trying to calculate. But to calculate it, we need to consider the dilution first, before the hydrolysis. So you need this equation to calculate the concentration of the diluted entities. You need to know the concentration of the dilute of this thing, the conjugate base. But what is that thing? Well, the volume, I know, we have 20 milliliters of this. Okay, it came from the acid, so we have 20 milliliters of that. That would be the sample. We need to divide by the total volume after the dilution. Well, it is basically the sample plus the amount of titrate you added, which is 20, so it's 20 plus 20. The question is, what is the concentration of the acetate in the original solution before you dilute it? What is the concentration? Well, because we're now at the equivalence point, and the definition of the equivalence point is all the acid and base have been consumed, well, we can safely assume that whatever conjugate base you have now all came from the original acid. All of the acid have been converted to the conjugate base. So the concentration of the base should equal to its conjugate acid. The initial concentration of the acid given to you by the question, which is 0.3 moles per liter. Okay. Every single one of them have been converted to the base, so the original concentration should be the same thing. Can you sub this in? 0.3 molar before you dilute it, times the volume, 20 milliliters. Again, before you mix things together, you have 20 milliliters. Divided by total volume, which is 40, you get 0.150. This is the concentration of the conjugate base that undergoes hydrolysis. After you mix the two solutions together, you dilute it. Okay, does that make sense, folks? This can get a bit confusing because there are many reactions happening at the same time. Do you guys follow? Okay, once you get this number, this is the diluted concentration before hydrolysis. So technically, this is the initial concentration for this ice table. You can finally calculate the ice table. Okay, the first row, initial concentration of the base, 0.150. We calculated this just now. Initial concentration of the product, 0. It didn't hydrolyze yet. Okay, that is initial, non-equilibrium. Of course, you will use X for the change. And finally, equilibrium, you just add up the first two rows. Then we can calculate the hydroxide produced with this equilibrium and then use that to determine the pH. The hydroxide created by this equilibrium far exceeds the hydroxide from the autoionization of water. Autoionization gives you 10 to the negative 7. That is pathetically low. We can just ignore that number, just focus on the hydroxide produced here. We have the Kb, we calculated that. We have the ice table, we calculated this. We can solve for X with the Kb and the ice table. Okay, of course, you would do the assumption. Why would you not? You justify, well, 0.150 divided by 10 to the negative 10, that is like a billion. Okay, that's way greater than 100. So yes, we are safe in this assumption. You drop the x, you can now rearrange and solve for x. Using the calculator, x is approximately 9.129 times 10 to the negative 6. Okay, we clear about that? What is x? According to your ICE table, x is the amount of hydroxide. So you've solved for the concentration of hydroxide at equilibrium after you mix them together after hydrolysis. Okay, this is the final thing that we want. Negative log of this guy gets to the pH. So the pOH is negative log of hydroxide. The pH is 14 minus that. So 14 plus log of hydroxide. Finally, punch this in your calculator, you get 8.96. So the pH of the sample at the equivalence point, where all the acids have reacted with the base, is not 7, but it is 8.96, slightly basic. You see, that was a long calculation. We eventually arrived at this number. I just want to note that the pH of the equivalence point between a weak acid titrated with a strong base is always going to be greater than 7. It is always going to be basic. Okay, now why is it basic? Well, because you have a weak acid. After you react all of those, you will become the conjugate base, and the conjugate base will accept protons from water to establish a new equilibrium, and that produces hydroxide. So thus the overall pH is basic. Okay, that is the explanation here. What is a fast way of remembering this? Here's how I remember this. It's a weak acid with a strong base. Acid is weak, base is strong, base is better than acid, so therefore it's going to be basic. Okay, that's my shortcut in remembering that this pH should be greater than 7. That is by no means the explanation. That is not why it is greater than 7. It is just a shortcut for me to remember that it is greater than 7. So if on the test I ask you to explain why it's greater than 7, you better not tell me it's a weak acid and a strong base. You have to explain using the hydrolysis and the equilibrium. Okay? Questions? Okay, that seems like good news, right? Last one, C, beyond the equivalence point. This is exactly the same as strong acid, strong base. So you need to determine the concentration of the excess hydroxide that you've added, and that determines the pH. Okay? Whatever other sources of hydroxide, like hydrolysis of the conjugate base, it's still there, but the equilibrium is shifted so far to the left, pretty much is non-existent. And also, the auto-ionization of water, we've just been ignoring that since day one, so again, it doesn't matter. This is the only thing that matters. The sodium hydroxide is producing a lot of hydroxide. What is the concentration of that new hydroxide? Well, we have these numbers, we can calculate that. We've added 35 milliliters, right? And we only need 20 milliliter. We have 35, only 20 is needed to reach the equivalence point. So you've shot over by 15. You have excess of 15 milliliters of base. We have the volume of that, but we need the moles. Well, easy. Volume times concentration is moles. How many moles of sodium hydroxide do I have in excess? Well, just multiply that with the concentration of sodium hydroxide. And that should give you 4.50 times 10 to the negative 3 moles. Okay, that's the amount of excess base that I have. To calculate the pH, I can't use mole, I must use concentration. So I take this mole, I divide by the total volume of my solution. So mole per volume. Mole, I just calculated. What is the volume? Well, you have 20 of the acid, 35 of the base, and you add them together, you get 55 total volume, and of course you have to convert to per liter. That's what you multiply by 1,000 milliliters per liter. You cancel the milliliters. You have 0.0818 moles per liter. Okay, that is the concentration of the excess amount of hydroxide. That's the concentration that you added too much of. So that determines the pH. Negative log 14 minus the pOH. You sub in the number, you should get 12.913. 3 sig figs, 3 decimals. Okay? If you just look at this number, it's almost 13. That's quite high for pH. Of course, it makes sense because you added way too much hydroxide. So basically, you have a strong base solution now. The pH is going to be high. All right, so this is, again, no different from the calculation that you've been doing for strong acid and strong base beyond the equivalence point. If you check out the titration curve, well, it looked very similar to the titration curve for strong acid, strong base, but with some differences. First of all, the most glaring difference, the equivalence point. The pH is not 7, it is 9. Okay, it is a basic pH because it's a weak acid with a strong base. Also, on its way to the equivalence point, you go through a zone that has a really flat slope. All right, we call this the buffer zone. Why? Because it has the buffering effect. There is a whole lesson on buffers that I don't think I'll have time to cover, so unfortunately I just removed that from the course. Just here's a little quick lesson on buffers, if you will. What is a buffer? A buffer is an equilibrium that seeks to minimize any change in pH. If you want to change the pH of something, you can add some acid or base, the pH should change. But if you have a buffer present, the pH will change by a very small amount. This is very classic. It's in your blood. Inside of your blood, you have an equilibrium with the bicarbonate ion and carbon dioxide. That's an equilibrium with each other. That's a buffer. The pH of your blood must remain at a constant number, 7.35. Otherwise, you go unconscious and then you die. Okay? If you drink lemonade, that is not suicide because the acid from the lemonade is not going to change your blood pH because of buffers in the blood. So you drink a lot of lemonade. You bring the acid into your bloodstream. So you have an increase in the amount of hydrogen, H3O. Wouldn't that make your blood more acidic? Well, no. Because of the equilibrium you have, Le Chatelier's principle will shift that buffer equilibrium to produce more hydroxide to counteract the acid, so it remains the same. So that's why you can eat all the food you want, you're not going to change your blood pH. Okay, it has to stay the same because of buffer. So because this titration, you have a weak acid that is in equilibrium with its conjugate base, it is very hard to change the pH because of Le Chatelier's principle. You add some base, cool. You remove some of my acid. Well, don't worry, Le Chatelier's principle would shift the equilibrium to produce more acid, so the pH changes very little until you run out of acid. You can only shift the equilibrium to the left to the right by a certain extent. Once you reach that limit, that reaction will reach completion. Goodbye, equilibrium. Without an equilibrium, you don't have the buffer effect anymore, so the pH shoots all the way up. Does that make sense? So when you see a titration curve, you have to note that where is the equivalence point? Okay, where did it start? Well, it starts with a very low pH because you have an acid, and then you flatten off because of the buffering, and then you shoot all the way up because you become a base. All right, so make sure you know how to interpret a titration curve of weak acid, strong base, as well as strong acid, strong base, and later we're going to learn a weak base, strong acid. Any questions about that? All right, so here is example 3, which is our last example for the day. It is the opposite of what we just did. You have a weak base titrated with a strong acid. Same idea, except now the hydrolysis is with the conjugate acid. Okay. The base will become the conjugate acid, and you will produce hydronium instead of hydroxide. So here is a new example. The titration of 20 milliliters of 0.1 molar ammonia with 0.1 molar HCl. Ammonia NH3 is a weak base. HCl is a strong acid. Okay, so it's weak base, strong acid. Calculate A, the pH before you add any acid. B, the pH at the equivalence point. And C, the pH beyond the equivalence point, specifically when 40 milliliters of HCl is added. You have the balanced equation, NH3 plus HCl, you have NH4 and Cl. Okay, that you know. And let's, and you have all the information here. So let's look at the pictures to help you understand this. Here we go again. It's the same thing you saw. In the first row, before titration, you didn't add any acid. You just have the ammonia NH3 in water. Okay, of course, the auto ionization of water is it happens everywhere in all of the panels. But the ammonia didn't reach equilibrium with the water yet. The panel on the right, on top, it did reach equilibrium. One of the ammonia accepted a proton from water. In blue, you have ammonium plus, with the 1 plus. And then you produce hydroxide. That reaches equilibrium. The solution is basic because of that hydroxide being produced. Okay, that is before titration. If you start to add the acid, you add just enough to reach the equivalence point. All of the ammonia, NH3, is consumed by the HCl. You would have chloride, Cl minus, and NH4 plus. Okay, on the left side in the middle, that's what you see. And a whole bunch of water molecules. This is the equivalence point. All the acid react with all the base. That's it. But this is pre-equilibrium. There is another equilibrium. What equilibrium is that? The ammonium, NH4, will react with water because ammonium is a weak acid. It will seek to donate protons to water, and it does. And it reaches equilibrium to the panel up to the right. In red, you have H3O and the conjugate base again, NH3. At the equivalence point, all the acid cancel with the base. The conjugate acid produced will establish a new equilibrium via hydrolysis. You have a new source of hydronium that determines the pH. That will make the solution acidic. Okay, weak base, strong acid at equilibrium at the equivalence point is acidic. Lastly, same story. Beyond the equivalence point, you added way too much acid. Whatever equilibrium you had with hydrolysis, well, that's been shifted all the way to the left. You increase hydronium, which causes the equilibrium to shift to lower hydronium, and you will also lower NH3. Basically, the final panel is what happens beyond the equivalence point. What will determine the pH? Whatever solution of hydrochloric acid did you add in excess, that will determine the pH. Nothing else matters. Okay, it's the same story, same idea as the base version of this, except it's with acid. Okay, so I will give you some time to try this one on your own. Refer to the previous example. If you're stuck, it is exactly the same. You need to practice. Okay, I'll give you ample time for this because it is quite long. Give you around 20 minutes. You might not need 20, so I'll come back in around 20 minutes to check. Try this on your own. Try to get the same answers as I do, and then I'll come back in 20. So let's actually solve example 3 mathematically. First thing, you have to calculate the pH before you add any acid. Now this one, all you have to do is calculate the pH of that weak base. which is quite simple. It's just ammonia, the base plus water. You have ammonium and hydroxide. That's the equilibrium that you need to calculate. Initial given to you, 0.1 molar. The products are obviously 0. Change is X, and then you add them up. The Kb of NH3 is not given, so you need the Kb. How do you calculate the Kb? Well, you need the Ka of NH4. You have to use Kw for that. The Ka of NH4 can be found on the table, and Kw is just a constant. If you plug this in, you should be able to get the Kb of NH3, which is 1.786 times 10 to the negative 5. Okay. Once you get the Kb, apply it to your table, your ice table, you sub in the X. You do the assumption, X is so tiny that 0.1 minus X wouldn't really do anything to justify. Well, the initial concentration, 0.1, divided by the Ka, which is 10 to the negative 5, you have a large number, so assumption justified. Drop the X, you isolate for the X, and you solve for the X. So X is 1.336 times 10 to the negative 3 moles per liter. All right, and X is the concentration of the hydroxide here. So all you have to do now is take the negative log of this number. You should be able to get the POH, and then subtract that from 14 to get the pH. So you should get 11.13 with 2 decimals for 2 sig figs. All right, did everyone get that? The pH of the ammonia, before you add anything, is 11.13, which makes sense. It's a base. B, the pH at the equivalence point. Okay, here is where it gets complicated. If you reach the equivalence point, all the hydroxide from the base are consumed, and all of the acid, H3O, from the HCl are consumed. So they cancel each other. What's going to determine the pH then? Well, hydrolysis. Somebody's going to hydrolyze. So you have to identify everybody that will hydrolyze, or that has the potential to hydrolyze. NH4, Cl, and then you have the H3O away from the auto-ionization of water. You don't have to consider those. Chloride, well, that's just the conjugate base of a strong acid. That's a spectator. So NH4 must be the entity that can hydrolyze. So that is a weak acid. It will react with water to produce NH3 and H3O. Okay, so it produces an acidic solution. It produces H3O plus. So you can do a dilution calculation. The dilution calculation will calculate the concentration of your acid after you mix things together, right? So you have the initial volume of your acid, which is 20, given to you by the question, divided by total volume. It is just the volume of the acid plus, the volume of the initial base, I should say, plus the titrant. But I don't know how many milliliters do I need in order to reach the equivalence point. You see, the question never gave me the amount of titrant I needed. So problem, I need to calculate the amount of titrant that I need. You can calculate the volume of titrant to reach the equivalence point just by treating this as a normal titration problem. You have 20 milliliters of base times the concentration of that base in moles per liter. You convert to milliliters to cancel. Right? It's a 1-to-1 ratio in the balanced equation, so those two cancel. So now you have moles of the HCl. You also know the concentration of that HCl, so you can easily calculate volume by dividing by that concentration. The moles of the HCl should cancel. And because I want the units to be in milliliters, because I'm using milliliters in my calculation, I multiply the final answer by thousands to get milliliters. So the titrant comes out to be 20 milliliter. I need 20 milliliters of the titrant to reach the equivalence point. So that must be 20. So I sub this in. It is 0.1, that's the initial concentration, times 20, that's the initial volume, over 20 plus 20. You mix the two together, you get 40, and you should get 0.0500. That is the concentration of the conjugate acid at equilibrium. You then sub into the ice table the concentration of the acid after the dilution, but before the hydrolysis is 0.05. 0 for the product, X denotes change, and then you will solve the ice table. Okay, you need the Ka, which you have, just look on the table, and then you have the ice table, X squared over 0.05 minus X. Solve for X with your assumption, and of course you can justify the assumption because it's 10 to the negative 10. You're going to have like 100 million as your answer. So yes, assumption justified, you drop the X, you isolate for the X. So X is approximately equals to the Ka times the initial concentration, take the square root. So X is 5.292 times 10 to the negative 6. You have to know that this X is H3O, which is perfect because negative log of H3O will solve the problem. That will get you the pH. Excuse me. So negative log of the H3O, you have negative log of just 5.292 times 10 to the negative 6. And finally, in your calculator, you have 5.28. This is the pH of the sample at the equivalence point. It is slightly acidic. In fact, all of the pHs at the equivalence point for weak-base strong acid titrations are going to be acidic, smaller than 7, for the same reason as mentioned earlier. Okay, if you have a weak base, well, when that reacts, it produces a weak acid, which will produce H3O at equilibrium, and the hydronium produced will make the whole thing acidic. Okay, the way I remember this, weak base, strong acid, well, acid is strong, base is weak, so it's got to be acidic at the equivalence point. I hope you got the same answer as me. Otherwise, check for your mistakes. Last one, C. If you go over, if you add 40 milliliters, okay, that's way beyond the equivalence point. What is the pH? So in this case, you just need to calculate the volume in excess. You added 40, you only need 20. How do I know that? I calculated this in the previous step. So I only need 20 to reach the equivalence point. So you would have 20 in excess. And how many moles in excess? Well, 20 the volume in excess times the concentration of the acid. And that will be 2 times 10 to the negative 3 moles. That is the amount in moles of excess acid you have after you add 40 milliliters. You need the concentration, not the moles. So divided by total volume. So it's the number we just calculated, 2 times 10 to the negative 3, divided by, well, 20 from the original sample. 40 is the thing you added, so you have to divide by 60. Times 1,000, because you need moles per liter, not per milliliter, and you end up with 3.43 times 10 to the negative 2. Okay, that base, and then you have some acid left, and that's just the pH of a strong acid. Any questions about this? No questions, we're good. Titration curve, well, is this just the opposite of the weak acid strong base one? The equivalence point, notice, has a pH of 5. All right, and instead this graph starts really high because originally you have a base with the high pH. As you add more acid, the pH decreases, and you decrease gradually at first because of the buffering effect, and then you drastically decrease near the neutrality point, and you level off again. All right, so you need to be able to recognize titration curves on the test. You won't be able to draw them. You have to interpret them. So we learned just one thing today: weak acid strong base titration or weak base strong acid titration. One of the entity is weak. If you have weak acid strong base, at the equivalence point, pH is 7 because the conjugate base will hydrolyze. Weak base strong acid, the opposite, at the equivalence point, pH is less than 7 because this time the acid will hydrolyze. Okay, so the calculations are quite complicated. Please make sure you get enough practice. And this is it for this lesson, and this is it for the course. Any final questions?
When is our test?
All right.